Okay, so the plan for today is to start chapter 6. We wrapped up chapter 5 last time talking about applications of systems of equations, and we're moving into chapter 6, starting on polynomials. And today the plan is just to cover 6.1 and see how much we get through 6.2 on addition, subtraction, and multiplication of polynomials and monomials and so on. The quote of the day today, I think we've had this quote before, but I think it's one of my favorite quotes, and I think it's a good one to remember around midterm time from my graduate professor, Professor Layton. Good decisions come with experience, and experience comes from making bad decisions. So particularly around midterm course grade time, you can go on to MyCCAC and look at your midterm course grades. You can see if your grades are kind of where you expect them to be, where you want them to be, or not. And I think it's also a good time to kind of look back at the first half of the course and ask yourself if things, not just in this course, but in other courses as well, have kind of gone the way that you wanted them to go. Maybe if you struggled a little more in an exam than you had wanted to, or something like that, didn't do so great on an exam in some course, maybe you can take that experience and use it as a learning experience and see, what you can do for, say, the next exam or maybe the next term paper or project, whatever it may be. What can you do differently in the second half of the course to leverage what you learned in the first half of the course? So I think that's really the benefit of midterm course grades is gives you a little bit of a chance to take some perspective on how the first half of the course went or is going, and if you want to change anything for the second half of the course. If you just kind of completely forget about the first half and plod forward, then any mistakes that you made, if you don't learn from them, they're just costly mistakes and they don't bring any benefit. So if you made any mistakes in the first half of the course, then learn from them. And if things have gone great the first half of the semester, then great, excellent. Then you don't have anything to really change or work on for the second half. Okay. So moving into the chapter 6 material, we're going to talk about adding and subtracting polynomials. And first, let's discuss some semantics, some details of what are the definitions of the words that we're talking about here. Okay, so we have a few words to start with, and they are monomial, binomial, and polynomial. And a polynomial is really a series of monomials that are added together. A monomial is a term, so this is a one-term polynomial in a sense. Mono kind of being related to one. Binomial, like bicycle, like two. This is a two-term polynomial. And a polynomial, we typically call it a polynomial when it's three or more terms, although monomials and binomials are special cases. So typically three or more terms. We'll call it a polynomial. Sometimes we refer to trinomials for three terms as well. But for instance, we might look at something like 3x squared. This is a single term. Why is it a single term? Well, because everything in it is just multiplied together. If the only operation we see is multiplication or division, and exponentiation is just repeated multiplication, so this is like 3 times x times x, then that's a term. If I look at something like 3x squared minus 2x, I see there are two terms here. There's one bit where everything is multiplied together, multiplied or divided. There's another bit where everything is multiplied or divided, but they're separated by an addition or subtraction. So this is one term, this is a second term. There are two terms here. So the first example, just 3x squared by itself, we might call that a monomial, say one-term polynomial. The second one with two terms is a binomial. It's a two-term polynomial. Or we might look at something like 3x squared minus 2x plus 1, which has three terms. We could call it a trinomial, but I think at this point it's at least as common just to call it a polynomial. We also have a question of degree. So the degree of a polynomial, of a monomial, binomial, or multi-term polynomial. Well, one thing that we saw up here is anywhere that I see my variable coming into play, anywhere that I see an x in this case, or whatever variable we might be using in a different problem, I noticed that it only comes in as x to a positive integer power. So my variable only appears as x, x squared, x cubed, etc. I wouldn't really call it a polynomial if I had like a square root of x in here, or like a 1 over x, or if I had like a sine or cosine of x or something like that. I wouldn't really call those polynomials. So one important note is that my variable, like in the examples above, only appears when I see it as x or x squared or x cubed. I do have a constant term here where I don't explicitly see a variable. That's allowed as well. But no, say, for instance, square root of x, no 1 over x, no sine of x, or anything like that. So the degree of a term is the power on x. So if I had a term like 3x squared, this is second degree. It has degree 2 because there are two factors of x in this term. And similarly, of course, if I had 3 times x, I would write that as 3x squared. That's still a second degree polynomial. So after I kind of combine all of my x's under an exponent, all of my powers of x under a single exponent, then it's the question of what is that exponent? That's the degree of that term. And the degree of a polynomial, well, that's the highest degree of any of its terms. So if we go back up here, this is a second degree polynomial. It's just a monomial, this 3x squared. This one is as well, because this first term has degree 2, the second term has degree 1. Remember that x by itself is really just x to the first power. And the third example is also second degree. Now, if I had a polynomial like, say, 2x minus 1, a binomial, this would be degree 1. My 2x term, this first term, it only has an x to the first power. X is just x to the first power, so its degree is 1. This constant term actually has no x's in it. But remember, kind of anything to the 0 power equals 1. So we really can think of a constant, like basically being 1 times whatever that constant is, or that's like x to the 0. So this would be a degree 0 term, the constant term. And then the largest of the degrees between 1 and 0 is 1. So this is a first degree polynomial. If I had something like 7x to the fourth plus 2x minus 1, well, this would be a fourth degree polynomial. The highest exponent I see anywhere on x, either explicitly or implicitly, right? This is like an exponent of 1. This is like an x to the 0 power for that constant. Well, the highest power I see anywhere is 4, so the degree is 4. So once we've kind of taken each term and got all of our x's combined together, then the degree of the polynomial is really just the highest power that we see attached to a variable. And a polynomial is the sum or difference of monomials. And a monomial is just a number times a variable to a power. And again, we are not considering things like square root of x or 1 over x. We're only considering variables to powers. That's the only way that we're allowing our variable to come into play here. Okay, so we might ask then, well, I have 3 terms here or 2 terms there. Is there any way to simplify things further? In these cases, like here or here, the answer is no, but sometimes the answer is yes. I mean, in the simplest case, of course, if I just had like 2 plus 3, in some sense, this is actually kind of a polynomial, isn't it? Like, I mean, I said that I can think of a constant as being like a number times x to the 0 power, because it could be a number times 1. So this is kind of like actually just a really simple polynomial, just 2 very simple monomials added together, and this is 5. Okay, so I see that, in this trivial case almost, I can definitely combine some monomials together with other monomials. I mean, I can combine constants together with constants. Does this extend at all? And the answer is yes, it extends. If I have 2 terms with the same variable or variables, we could generalize this to include more than one variable popping up. So I'll say variable or variables to the same power or powers. We call those like terms. And we can combine like terms together. We can take 2 monomials that are like terms, combine them together as a single monomial, and make things a little bit simpler to deal with. So let's look at an example of that. Oops. I don't know why my handwriting is so goofy these days, or this morning. All right, take 3x squared minus x squared plus 2x minus x plus 7 minus 2. I see this as a second degree polynomial. The highest power I see anywhere on x is 2, but it has like 6 terms at the moment. Can I make this simpler? It's still going to be a second degree polynomial, but can I get it down to less terms? Well, the first thing I might notice is that if I think of this just plus 7 minus 2, those are just 2 constants subtracted from one another. That should simplify. So 7 minus 2 should give me 5. But I also noticed that the plus 2x and the minus x, these are like terms because they have the same variable, x, to the same power, to the first power. And similarly, the 3x squared and the minus x squared, these are also like terms. They have the same variable, x to the same power, in this case 2. When I'm combining monomials that are, or terms that are like terms, I just add or subtract the coefficients. So it's almost as if I think of like x to the first power as being like apples, and I have 2 apples minus 1 apple. How many do I have left? I have 1 apple left. If I have 2 x's minus 1 x, how many do I have left? I started with 2, I took away 1, I have 1 left. So I do coefficient 2, and then minus 1 gives me plus 1x. But of course, when we have something like 1x, we usually don't write it that way. We usually just write it as x. So if our coefficient's 1, we don't really explicitly write the coefficient. So we'll just write this as plus x. That's a plus 5. And then similarly with the x squareds. The x squareds are like oranges, and I have 3 oranges minus 1 orange. I have 2 oranges left, or if I have 3x squareds minus 1x squared, I have 2x squareds. So they can combine together. Now, one thing that I like to do is I like to write my polynomials with the highest degree term on the left and then go down the line as I go to the right. So I have my second degree term to the left, my first degree term, and then my 0th degree term, my constant term at the end. And that helps me to really clearly see here that there are no more like terms. There are no 2 terms here that have the same variable to the same power, because this is a second degree term, this is a first, and this is a 0th degree term. They all have different powers. So there are no more like terms, and there's nothing else I can combine together. This would be like trying to combine together apples, oranges, and bananas. You can't really combine the 3 things together. So this process of combining all the like terms together, that's simplifying. When we have a polynomial in simplest form, like any of the ones up here, or like the one that we just got, we should only have a single term for each of the powers on the variable if we're dealing with one variable. Right. So when we're in simplest form, every term should have different variables to different powers than every other term. If I saw another x squared term floating around here somewhere, I would want to combine it with the 2x squared and work my way down to where I only have a single x squared term, a single x term, a single constant term. So I think this is one of those things that it's a little bit hard to explain abstractly, but you get more of a hang of it just working through some examples. So let's jump into a couple examples down here. Oop, I have an extra space there. All right, let's look at our first example here. Simplify this polynomial. I see kind of at the moment, we might call it something like a binomial. It has 2 terms. And I noticed that both of those terms have the same variable to the same power, y to the 3rd power. So these are indeed like terms. So these are like terms. And I can combine them together. I should be able to combine these 2 terms into a single term so that then I only have 1 term with y to the 3rd power. And again, if I have 7 of those and add 3 more of them, I just end up with 10 of what? 10y cubed. So I just add the coefficients together, the numbers in front of the variable to a power. I just add those together, and then I keep the same variable to a power. If I look at something like this, 3x minus x plus 4x squared, I see my 3x is x to the first power. It's a degree 1 term. My minus x is also x to the first power. So those two are actually like terms. But then my third term here, 4x squared, it's the same variable, but it's a different power. So it's not a like term with the other two. I should be able to combine the 3x and the minus x together, but the 4x squared is just going to kind of stay by itself. So if I have 3x minus x, if I have 3 of this thing minus 1 of it, I have 2x. That takes care of these first two terms. I've simplified those down into a single term. And then my 4x squared, there's nothing really for it to combine with, so it just comes down. Plus 4x squared. And I can see that in what I have left, each term has either a different variable or a different power. In this case, it's all the same variable, but they have different powers. The first power versus the second power, they're not like terms, they cannot combine together, and this is fully simplified. And then let's look at one more example. I could actually add two polynomials together. Up here, I was kind of phrasing this as like maybe two monomials added together or three monomials added or subtracted from one another. But I could think of adding or subtracting polynomials from other polynomials. Nicely enough, as long as we're careful with order of operations, it pretty much works the same way as just adding a bunch of monomials together. Basically, what I would do is just break my first and second polynomial here into their component monomials, rearrange, and then just add the monomials together to get a simplified polynomial. So I just think of this like 5x squared minus 4x plus 3. Like I'll think of it as three monomials instead of one big polynomial, 5x squared minus 4x plus 3. And then I just want to add two more monomials to that, plus 3x squared minus 1. I just think of these, it's just kind of like breaking them out of a little like shell or something and breaking them into the component pieces. And then I'm going to reassemble them in a way that's convenient for me. Now, one thing I know is that addition is commutative. So a plus b is the same as b plus a. And subtraction is like a little bit commutative. That's probably not a good way to say it, but I can move subtraction around like this minus 4x I can move as long as I take the minus sign with it. So like a minus b is the same as negative b plus a. As long as I keep that negative attached, I can kind of move the position. Right? And really, I'm just using the commutativity of addition there. I'm making, say, a minus b. I'm thinking of that as a plus negative b, and then commuting the addition. Okay, but I see that I have some degree 2 monomials, the 5x squared and the 3x squared. I have some degree 1 monomials, this negative 4x and this, just have one of those. And I have two degree 0 monomials, two constants, the plus 3 and the minus 1. Let me put the degree 2 monomials up front. 5x squared plus 3x squared, that takes care of both of those. We'll go to the degree 1 monomial, minus 4x, just making sure that I bring that minus along with that coefficient of 4. And then down to our constants, plus 3 minus 1. Now I can take my first two monomials that are degree 2. These have the same variable with the same power. These are like terms. I have 5 of them, and then plus 3 more. I have 8 total x squareds. My degree 1 monomial, my linear term, as it's often called, is minus 4x. It has no other degree 1 monomials to combine with, so it just comes down minus 4x. And my degree 0 bits, or my constant terms, the plus 3 minus 1, we just add those together. 3 minus 1 is 2. We get plus 2. And we do one last check. Do I have any other terms that have the same variable to the same power? No, I don't. The first one has a second power, the second one has a first power, and the last one has no visible x's, or we can think of that as like x to the 0 power. No more like terms. This polynomial is simplified. So we've simplified it down into a trinomial, or into a 3-term polynomial that's of degree 2. Okay, let's work a couple of exercises. Oops. Trying to space these out just a little bit. Let's work a couple of exercises. Maybe take about 2 minutes to work through these. Shouldn't take very long. And then we'll come back and discuss the answers. So we'll be back in just about 2 minutes. Okay, let's take a look at the answers for these two. So I think these should be pretty straightforward. So the first exercise here, 12x to the fourth plus 9x to the fourth, we note that both of these terms, both of these monomials are degree 4, and they have the same variable to the same power, so they are like terms. They should be able to be combined together. And to combine them together, we add the coefficients, 12 plus 9. We get a new coefficient of 21, and that's attached to the same old x to the fourth that we had before. So 21x to the fourth, the answer to the first exercise. Second exercise, a little bit trickier. Here we have 3 terms. We see our 5k term is a degree 1 monomial. 7k cubed is degree 3. Minus 2k is degree 1 again. So our degree 3 term is kind of stuck by itself. It has no other like terms to combine with. It just kind of comes down. We just copy it down, 7k cubed, and that takes care of that term. Our two linear terms, our two monomials that are of degree 1 that have k to the first power, just k, those are like terms. They have the same variable k to the same power, the first power. So then I add or subtract their coefficients. I have 5k minus 2k, 5 minus 2 is 3. So that gives me 3k when I combine those two monomials. And again, I take one last look through. I have a k cubed term and a k term. They don't have the same power. So there are no like terms left. I can't combine anything any further. And this is my answer. Okay. So let's look at another exercise or another example here and then a similar exercise. Now this example is stepping up the difficulty just maybe another half a step. There's really two new things going on here. One is we have to be really careful with our order of operations. In theory, this shouldn't be something new. We know how order of operations work. We know how distributing negative signs and things works. But the thing is, anytime that you take kind of material that you've previously mastered and you apply it in a new scenario, sometimes that previous ability degrades a little bit, right? And this goes for anything that you do, right? If you're whatever, if you're like an athlete and you're playing some sport and you're pretty good at it, and somebody says, "Oh, okay, you're playing basketball. Here, try something a little bit different on your shot or something like that." Or you're playing baseball, try something a little bit different on your swing. Well, now you're focused on, well, I need to do this new wonky thing with my swing, and it feels a little funny. And all of your other performance abilities go down a little bit because you're focused on this new thing now, right? So it's easy to make mistakes like just forgetting about order of operations or not being careful about distributing things properly. And the other kind of hitch thrown in here is we actually have two variables now. So here we have a polynomial with two variables, m cubed plus n squared minus 2mn. We want to take 6 times that polynomial minus the polynomial 2m squared plus 3mn. Now, one thing to note, it doesn't really come up here, but just as a little side note, that say m times n is the same thing as n times m. If we had like one of these terms written as mn and the other one written as n times m, the other way around, they're the same term. They're like terms. They have the same variables, m and n, to the same powers, the first power each. It's still the same. They're still like terms. So just if they look a little bit different, if it's the same variables to the same powers, they're like terms. Doesn't really apply to this case directly, but something like that could come up. Okay, so what's my goal here? My first goal, my first like kind of intermediate goal is to break all of this into just a bunch of monomials. When I looked at my previous example where I was adding two polynomials together, breaking everything down into just monomials allowed me to move the monomials around and combine them together, made everything a lot easier. So let me try to do that here. So I have 6 times this first polynomial that has 3 terms. We might call it a trinomial or a 3-term polynomial. The 6 has to distribute into each of these terms. So I have 6m cubed plus 6n squared. 6 times minus 2 is minus 12mn. And here's a part where it's really easy to make a mistake. This negative has to distribute to both terms. Really, minus 2m squared plus 3mn is really plus negative 1 times 2m squared plus 3mn. And then we can see more clearly that that negative 1 factor is really what's distributing in. But often we just say distribute the negative. I mean, that's a little bit loose with the wording, but it's accurate enough. Right? Most folks would get the minus 2m squared, but especially in the context of, we're trying to do all this stuff with polynomials and monomials, and it's a little confusing. It's easy to forget that this 3mn also needs to be changed to a minus 3mn. Okay, now I go through and try to figure out what are my like terms. I have 6m cubed. If I look through all of my other terms, there are 5 terms here. If I look through the other 4, do any of them have just an m to the power 3? Actually, no, I think this is the only one. So we'll bring it down. What about 6n squared? Does any other term have n to the power of 2? No, I don't see anything. So we'll bring it down, plus 6n squared. What about the minus 12mn? Does anything else have m to the power 1 and n to the power 1? Actually, yeah, I do see another one of those, minus 3mn. These two are like terms. I can combine them together. I have minus 12 of them and then minus another 3. That's minus 15mn. And then lastly, I have minus 2m squared. Of course, that is the last term, so it has nothing else to combine with, minus 2m squared. Now I look back over these 4 terms and I ask myself, are there any 2 terms that have the same variable to the same power? There shouldn't be, but I might have missed one. I might have made a mistake. Do I see the same variable to the same power anywhere? No, I don't. I see the same power, 6n squared and minus 2m squared, but they have different variables. Or I might see the same variable, like 6m cubed and minus 2m squared, but they have different powers. So no 2 terms have the same variable or variables to the same power or powers. So that's our simplified form. That's the best we can do in this case. We can't get anything simpler than this. So this is one of those problems that it's, just going to be kind of inherently a little bit more complicated because we got 2 variables floating around and we've got degree 3 terms and so on. So that's the simplest we can get. Okay, let's take a look at 2 exercises. One that's not too bad and one that's a bit more challenging. So give these 2 exercises a shot. Maybe take about maybe about 3 minutes or so for these. I think they should go fairly quickly. So we'll take about 3 minutes. We'll come back and discuss the answers. Okay, it's just about 3 minutes. So for our first one, the main thing we have to be careful about is distributing this negative sign properly. So I break up, I think of this as the difference of two polynomials, one polynomial minus another polynomial, but I want to break those up into individual monomials that are all added or subtracted so that I can rearrange them as needed. So I just break up this first polynomial into negative 2x squared plus 3x minus 1. And then I distribute the negative through to get minus 7x squared and then plus 3. The minus out in front changes the sign on the 3. And I go through and I see that minus 2x squared, it has a like term in minus 7x squared. So I can kind of put those two together out front here. 3x, well, that doesn't have any other like terms. I'll just put that next, my linear term, my first degree term. And then my constant terms, minus 1 and plus 3, those are also like terms. I'll kind of push those to the end. And then I combine my like terms. I start with the x squares, my second degree terms. Minus 2 minus 7 gives me minus 9x squared. My plus 3x doesn't have anything else to combine with. It just comes down, plus 3x. And then minus 1 plus 3, my new constant term would be plus 2. And I take one last look over my answer here, negative 9x squared plus 3x plus 2. There are no like terms remaining, no terms that have the same variable to the same power. So this is simplest form, and that's my answer. In the second exercise, the first thing I need to do again is break this into a bunch of individual monomials. So I distribute the 2 first to get 2m cubed. Oh, and I missed a 2 there. Plus 2n squared. And then minus 6m. And then to that, I'm just adding this other polynomial, minus 5m squared minus 2n squared plus m. And then I go through and I look for like terms. So my first term, 2m cubed, are there any other m cubed terms? I don't see any. We can just bring that one down, 2m cubed. My next term, a 2n squared. So 2n squared, are there any other n squared terms? Well, yeah, there's one here, minus 2n squared. I get 2n squared minus 2n squared. That gives me like 0n squared. But if I have 0 of something, I usually just don't write it. So I would just omit those, or I might go up here and just kind of cross them out like this because they cancel. Okay, my next term that's, so I've taken care of this one. I've taken care of these two. My next one in line is the minus 6m. That's an m to the first term. Do I have any other m to the first terms? Yeah, I do. I have a plus m. So minus 6m plus m, minus 6 plus 1, negative 5. So minus 5m. And then my m squared term, I don't have any other m squared terms to go along with it, minus 5m squared. And this would count as simplest form. I might go ahead and, just because of the way that I like to write things, kind of write it in decreasing order of the powers, especially if I was going to continue on and use this to do something else with it. Having it structured this way just helps a little bit. Just helps a little with pattern recognition, or with reducing errors, with being less likely to mistake one power for another, or to forget copying something down or something like that. But this would be my final answer, 2m cubed minus 5m squared minus 5m. But writing it this way would also be perfectly fine. Okay, so addition, subtraction of polynomials, really not too difficult. The main challenge here is identifying like terms and combining like terms together. And then in the context of dealing with polynomials and letters and variables and all of this, just being really careful with things like order of operations. Okay, so let's move on to section 6.2, properties of exponents. So we have a few properties here. We have our product property that if we have the same base raised to an exponent, and we have a product of two of those, so x to the m times x to the n, that's x to the power m plus n. And this kind of makes sense, right? If I have x multiplied by itself m times, and then I multiply x multiplied by itself n times, overall, I just have x multiplied by itself m plus n times. So this kind of makes sense just by, in essence, like direct experiment, just kind of writing it out. What about our power property? X to the a to the b power. Well, x to the a to the b power, something to a power, something to the b power means multiply it by itself b times. But that just means I have a factors of x, and then a more factors of x, and then a more b times. I just have a times b total factors of x. That's x to the a times b power. So x to the a to the power b is just x to the power a times b. And our product to a power property, x times y all to the power m equals x to the m times y to the m. The power distributes over multiplication in this manner. Why is that? Well, it's because I have x times y times x times y and so on. And I have m of those. But multiplication is commutative, so I can push all of the x's up front and all the y's to the end. This is just x multiplied by itself m times y multiplied by itself m times, just leveraging the commutativity of multiplication, which is x to the m times y to the m. So if you ever are trying to remember these properties, or if you ever think, wait, how does x to the a to the b work? Is it like x to the a plus b or x to the a times b? I can't quite remember. Kind of just write it out and count how many factors of x you end up with. So if you ever get confused between these properties, just write it out and just, count how many factors you have of each thing. Okay, so what if I have something like this? What if I have what amounts to two monomials, say 3y squared, we could think of that as a monomial, and y cubed, we could think of that as another monomial. What if I have those multiplied together? We talked about how to add or subtract them in the last section, but I can kind of think of this like two monomials multiplied together. How does 3y squared times y cubed simplify? Well, the first thing I notice is that this is really just 3 times y squared times y cubed. Multiplication is associative, so I can choose to multiply the y squared and the y cubed kind of together and leave the 3 out front. And I see that my product property comes into play here. I have the same base, y, to two powers, right? Y squared times y cubed. Well, I add the powers. Why does that make sense? This is basically 3 times y times y times y times y times y. There's just 5 factors of y there. We could, do this by brute force that way, or we could use our product property. I don't know why I left myself so much space between these. Well, What about this example? Simplify 2x squared times 3x cubed squared. So this would be like maybe a monomial times the square of another monomial. Well, I think the first thing I probably want to do is work with this one. Why? Well, if I started here with the product of the two things, I would probably want to use the product property, but I don't really have the same base yet, right? It's not like I have something to the first power times the same thing to the second power. I have something to the first power times something different to the second power. So I need to, I think, start by simplifying this bit here using my power property. 3x cubed squared, or I guess it's really our product to a power property that we're going to use first. This is 3 times x cubed squared is 3 squared times x cubed squared. 3 squared is just the number 9. And x cubed squared, now we're using our power property. X to the 3 times 2 is x to the 6th. Now I can bring this back over. And I see this simplifies to 2x squared times 9x to the 6th. And now I would like to use my product property. But again, I need the same base to some exponents multiplied together. So I need to rearrange things a little bit more. I think of 2 times x squared, or I think of 2x squared as 2 times x squared. And that's multiplied by, I think of 9x to the 6th as 9 times x to the 6th. Multiplication is commutative, so I can write this as 2 times 9 times x squared times x to the 6th. And 2 times 9 is 18. And then I look at x squared times x to the 6th, and this does fit the pattern for the product property. X squared times x to the 6th should be x to the 2 plus 6, or x to the 8. So 18x to the 8th. I have no other factors of x I can combine together. Nothing I can do to simplify any of the constants or anything like that any further. 18 is just 18. So 18x to the 8th is my answer for this problem. And then what happens if I'm multiplying two monomials that have more than one variable? Well, this actually isn't too difficult of a scenario. I do kind of what I did before. I think of negative 2m cubed as like negative 2 times m cubed. And that's times 3m squared n. That's like 3 times m squared times n. And now I just put all of my constants together, all of my m's together, and all my n's together. So I have like negative 2 times 3. That takes care of my constant factors. And then I can think of times m cubed times m squared. That takes care of my m factors. And then times n, taking care of that last n factor. I can multiply negative 2 times 3, that's negative 6. I can multiply all my m's together, m cubed times m squared. That fits into my product property. I have 3 factors of m multiplied together, and then 2 more. That's 5 total factors of m. And then just times n. There's nothing I can really do with this n to combine it with the m's. So it just is here at the end. So negative 6 m to the fifth times n. That would be our answer here. Any questions so far? Okay, let's work through these couple of exercises. And again, I think these should go pretty quickly. Maybe it will take 2 minutes, maybe 3 minutes, and talk about the answer. Okay, let's discuss the answers for these two. So for the first exercise, simplifying 2y to the fifth times y to the seventh. So again, we can kind of think of this as two monomials multiplied together. We first split this up into different factors, 2 times y to the fifth times y to the seventh. And then we think about y to the fifth times y to the seventh, and we can do some work there. We have our product property, x to the m times x to the n equals x to the m plus n. Or y to the fifth times y to the seventh would be y to the 5 plus 7 or y to the 12. So I should just bring down my 2, and then I have 2 times y to the 12th. Or we could just write this as 2y to the 12th. That will be our answer for the first one. There's nothing more we can do to simplify this any further. For a second one, again, a little bit more going on here. Basically, I have something like a monomial multiplied by a monomial raised to the fifth power. Let me take the more complicated piece first, the 2x squared to the fifth power. And I have my x times y to the m equals x to the m y to the m, my kind of distributive property for exponents over multiplication. So if I think of 2x squared as 2 times x squared, all to the fifth power, that can be simplified to 2 to the fifth power times x squared to the fifth power. 2 to the fifth power is 32. 2, 4, 8, 16, 32. Just multiplying that out. And then I have x squared raised to the fifth power. I have my power property. X to the a to the b power is x to the a times b power. Or x squared to the fifth power gives me x to the 10th power. So this bit here all boils down to just 32x to the 10th. But I don't want to jump ahead and think that I have the answer yet. I still need to take care of this first factor, the 5x cubed. So I need to bring this 32x to the 10th back over, and I get 5x cubed times 32x to the 10th. And again, I can kind of think of this as like two monomials multiplied together, but really 5x cubed is like 5 times x cubed. I can split those factors apart, and same for 32x to the 10th being like 32 times x to the 10th, splitting those factors apart. Using the commutativity of multiplication, I have 5 times 32 times x cubed times x to the 10th. 5 times 32 is 160. And then x to the third times x to the 10th. Once more, using our product property, gives me x to the 13th. So 160 times x to the 13th, or I could write that just as 160 x to the 13th. And that's my answer for the second one. Any questions on either of these? Okay, let's look at this problem. We have what here really is a monomial. It looks kind of complicated, but it's kind of a monomial. Well, it is a monomial. It has two different variables, x and y, to two different powers, multiplied by a coefficient that's a fraction. So there's quite a bit going on here. We have a fraction for the coefficient. We have two different variables, but this is a monomial to the sixth power times another monomial, 4 times x times y, each of those variables coming in with just the first power, to the fifth power. So I think what I probably want to do here is take my first monomial, simplify it, take my second, or my first monomial to the sixth, I should say, simplify it, take my second monomial to the fifth power, simplify it, and then bring them all together at the end. So I might be a little bit stuck immediately with this 1/2 x squared y cubed to the sixth power. I might look at this and say I have three things multiplied together raised to a power. But my property only says what to do with two things multiplied together raised to a power. Well, nicely enough, this property generalizes to multiple things multiplied together, multiple factors multiplied together raised to a power. So I could just make this 1/2 to the sixth power times x squared to the sixth power times y cubed to the sixth power. But let's do things a little bit more carefully than that. I'm actually going to think of 1/2 x squared like one factor and y cubed like the other factor. So I'm just breaking off y cubed. So now I really do have something that fits directly into the mold of my property, right? I don't want to get too fast and loose with, my property says this, but it feels like this should be true. That's not really mathematical thinking. That's not really precise enough. It would turn out to work out okay here, but there are a lot of cases where something feels like it should generalize or feels like it should be true and ends up not being true. So we do want to be careful and stick directly to our properties. Our property said that if we have the product of two things raised to a power, that power distributes over the two things. Well, this tells me that by my property, I have 1/2 x squared to the 6th power times y cubed to the 6th power. But now the 1/2 x squared, we can think of it as just the product of two things, 1/2 times x squared to a power. And now I can do 1/2 to the 6th power times x squared to the 6th power times y cubed to the 6th power. This is kind of a common theme in a lot of, well, maybe not a lot, but certainly not a majority of algebra problems, but enough that you see this theme or this pattern pop up, that if something works for two things and you think that it feels like it should work for three or four things, a lot of times this is the way you do it. You kind of take your four things or your three things and you write them as like one big thing plus one small thing, and you split those two things apart, and then you take your slightly less big thing and you write it as one even smaller, even less big thing times one small thing, and you break those apart. So you kind of just split the pieces off one by one. So if we want to really carefully use our properties, this kind of a theme comes up over and over. Okay, let's take a look at 4xy to the 5th power now, and we'll do the same thing. So I think of 4x times y to the 5th power. That's the product of two things to a power. This gives me 4x to the 5th power times y to the 5th power. And that 4x I can think of as 4 times x. 4 times x to the 5th power, that's a product of two things to a power. This is 4 to the 5th power times x to the 5th power times y to the 5th power. And I know I want to multiply these two things together. So coming all the way down here, I have 1/2 to the 6th power times x squared to the 6th power times y cubed to the 6th power times all of this stuff, 4 to the 5th power times x to the 5th power times y to the 5th power. All right, so I've taken my first line here and rewritten it this way. It seems like I've made it much messier, but actually we're going to see a lot of stuff combines together now. Maybe the next thing that I will do is start simplifying some of the factors in this first half here. So I have 1/2 to the 6th power. Well, 1/2 to the 6th power is like 1/2 times 1/2 times 1/2 6 times. That's 1/32. X squared to the 6th power, that's power to a power, the power property. This should give me x to the 12th. Y cubed to the 6th power should give me y to the 18th. And then I have times 4 to the 5th power. I think I'll actually leave it as 4 to the 5th times x to the 5th times y to the 5th. Now again, let me use the commutative property of multiplication. Let me take my constant factors, maybe put them first. And then I'll take my x factors, put them next. And then my y factors, put them last. My constants can multiply together. Let me come off to the side here. Maybe I'll keep my color scheme the same. 1/32 times 4 to the 5th. Well, I know from just kind of arithmetic and the way fractions work, when I have an integer times a fraction, I can make that 4 to the 5th over 32. I can multiply the numerator by the integer. And really, this is like 4 times 4 to the 4th over 32, but 32 has a factor of 4. in it. So it's like 4 to the 4th over 8. Or I can pull out another factor of 4. This is like 4 cubed over 2. Or this is like 4 times 16 over 2. But that's just 2 times 16 or 32. So this whole constant term, or sorry, this whole constant factor, 1/32 times 4 to the 5th turns out to just be the number 32. That kind of does make sense. 4 to the 5th, another way we could think of this, we could actually use our exponent property. Four to the 5th is like 2 times 2 to the 5th. Or that's, I guess I don't need another parentheses. That is 2 to the 5th times 2 to the 5th. But 2 to the 5th is 32. So 1/32 times 32 times 32. And I see that one of these 32s gets divided out and the other one sticks around. Okay, so my constant factors all just boil down to 32. Whether I did it maybe a little bit of a more slick way using exponent properties, or whether I just put everything into the fraction and started dividing out common factors, whichever way worked, it got us to the same answer, 32. Then our x's, we have same base to different powers. So I multiply those together, I get the same base to the sum of the powers, x to the 17th. And then for my y's, again, I keep the base and I add the powers. 18 plus 5 is 23. So I have 32 x to the 17th, y to the 23rd. So there were a lot of steps to this problem to get it fully simplified. But I don't think any of the steps was super challenging or super difficult, right? The main challenge, well, there were two main challenges. One was making sure that we remember our properties and that we use them carefully. And the other was just kind of taking our time with what I sometimes call the bookkeeping, like just making sure that we copy everything correctly from line to line, making sure that we're just careful about our arithmetic. I don't want to do like, 6 times 2 equals 8 or something like that, make silly arithmetic errors. That kind of stuff happens all the time when you're in a more complicated context. Again, you're kind of you're in a more challenging scenario because we're learning about polynomials now. So then sometimes those basic arithmetic skills can fall by the wayside a little bit because you're focusing on something else. So just making sure that we don't make those kind of silly mistakes. And yeah, just being careful with the order of operations, with all the arithmetic things, and making sure to use our properties correctly got us the answer, right? And just taking it one little step at a time. I didn't have to see at this point what the whole strategy was. I just kind of asked myself, is there something that I can do? Yeah, one thing I can do is start working on this piece and simplify it down. Is there something else I can do? I could work on this piece and simplify it down, right? So just chipping away little by little. I didn't have to see the entire path from A to B, from beginning to end at the beginning. Sometimes that can cause students to have a little bit of a challenge getting started. But if you find yourself there, if you're saying, I don't know where to start, well, just ask yourself, is there something I can do, right? Is there, I see that I have some things with powers to a power. Can I start by just using my power property? Okay, so two last exercises before we wrap up for today. And we'll take maybe about actually maybe 5 minutes or so, because this one just has a lot of pieces to it. A lot of operations need to be done. Again, I don't think it's really conceptually very difficult, but it's just doing a lot of things and being careful, taking your time going through them. So these two exercises will take about 5 or 6 minutes. Come back and discuss the answers in 5 or 6 minutes. Okay, it's just about 6 minutes, so let's talk about these two. So the first exercise, more straightforward one, just simplify negative m squared times 6m cubed n squared. And the one thing to realize here is that negative m squared, it might benefit us a little bit to write it as negative 1 times m squared. That's what I have here. And then the 6m cubed n squared, we'll think of that as 6 times n, 6 times m cubed times n squared. And now that everything is multiplied together, we can use commutativity of multiplication to kind of push that 6 all the way up front. So we get negative 1 times 6 times m squared times m cubed times n squared. Negative 1 times 6, just multiplying those numbers together gives me negative 6. The m squared times m cubed, I use my product property to get m to the power 2 plus 3, or m to the 5th power. And then the n squared doesn't really have any other n's to combine with, so it just stays as an n squared. And there's nothing more we can do here. This is the simplest it can get. Okay, now let's look at our second exercise, definitely the more the lengthier of the two. So this is pretty similar to our last example we did. So I have a monomial cubed times a monomial squared, and I want to simplify that whole thing. Let me start with the first monomial, the one that's getting cubed. And I can think of that as 1/3 times x to the 4th times y squared. That's all cubed. And again, I saw last time I as effectively proved, I just have to generalize it a little bit for a formal proof, that I can distribute the exponent through as many factors as I like. So here, this 1/3 times x to the 4th times y squared all cubed can break up into 1/3 cubed times x to the 4th cubed times y squared cubed. 1/3 cubed, 1/3 times 1/3 is 1/9, and 1/9 times 1/3 is 1/27. X to the 4th cubed, that's a power to a power. I multiply the powers, that's x to the 4 times 3, or 12 power. And then y squared cubed, y to the 2nd to the 3rd, ends up being y to the 6th power. So that's kind of as simple as I can get my first half of the problem, the first monomial cube. Now let's work on the other one, 9x squared y all squared. Well, I can think of that again as 9 times x squared times y all squared, which gives me 9 squared times x squared squared times y squared, or that's 9 squared times x to the 4th times y squared. And now I just bring these two back together, multiplying them all. 1/27 times x to the 12th times y to the 6th times 9 squared times x to the 4th times y squared. And again, I make use of the commutativity of multiplication. I can put my constant factors all out in front. I can put my y's all at the end and the x's in the middle. And I'm left with 1/27 times 9 squared times x to the 12th times x to the 4th times y to the 6th times y squared. Let's take a look at this constant. What is 9 squared over 27? Well, these both have a factor of 9 in them. This would be 9 over 3, or 3. 81 over 27 is just 3. So this is 3. X to the 12th times x to the 4th, that is our same rule as up here. So we add the powers. That is x to the 12 plus 4, or 16 power. And then times y to the 6 times y squared. Again, we add the powers. Y to the 8. There is nothing more that I can combine here. So that's my answer. That's the simplest form. All right. Any questions on anything that we talked about today? Any questions on 6.1 or 6.2? Okay, so one kind of side note, I would recommend that as we start moving into polynomials, this tends to be the material where um, the difficulty takes a bit of a whenever the difficulty increases a little bit here between kind of polynomials and factoring. So if you felt really good for the first half of the course, great, you're on a great track. But this might be a good time if you haven't already to maybe start reading ahead a little bit, maybe start blocking off a little bit more time, um, a little bit more study time and kind of bigger chunks, and hitting the books a little bit more, getting a little bit more practice in, a little bit more drilling in, something like that. Um, you know, so in preparation for next time, maybe read through, just kind of skim through the next couple of sections and yeah, just to prepare yourself a little bit better for the kind of ramp up in difficulty in these next couple of chapters. So I think that's a pretty good practice. Just there's the workflow document on Blackboard if you want to refer back to that for what a sample week might look like, but kind of skimming the material before it's introduced in class just helps you get a little more context. You don't have to completely understand it the first read through, but reading through the book before the lecture helps to just kind of prime things a little bit for the lecture so you have a little bit more familiarity with what's going to be discussed. That might make things like the exercises go more smoothly, particularly if you were struggling with the exercises or getting stuck a lot. This might be something to definitely to start doing at this point. Reading ahead a little bit, maybe even taking some notes, or if you have particular questions, if something just looks strange in the chapter or doesn't make sense to you, take notes and make sure that you either get that question answered during lecture, or if I don't answer it, you can ask it during lecture, or you can pop in office hours or send me an email. And then doing the homework, starting the homework fairly quickly after lecture that way. So if you've gone through the material once in the book, you've seen it in a lecture, you can go through it again in the book, do a couple more practice problems, and at that point, you should feel pretty good with that material, good enough to start doing the homework and actually assess how well you understand that material. So, yeah, I think at this point is where time management and being prepared ahead of time is super beneficial. All right. Well, with that being said, that's all that I had for today. So let me stop the recording.